Okay, I'm going to finish the last 3 questions in this lab. And the first question is, what causes some molecules to rotate light? So, I'm sorry, I'm just kind of leaving my camera on my notes here. But for that answer for question 1 is that there are 2 types of ways that you can describe molecules, and that's achiral and chiral. And achiral molecule is an object or molecule that is superimposable on its mirror image and has a plane of symmetry. And a chiral is just kind of the opposite. It is a molecule or object that is non-superimposable on its mirror image, and it doesn't have a plane of symmetry. So after reading some more into this chapter, I also found that a chiral molecule will cause rotation in the light, and that is because it interacts with the plane of polarized light, causing it to rotate a little bit. And in the lab, that's what I also is also what I'm measuring to do my calculations. And with the achiral molecule, it doesn't interact with the plane of polarized light at all, so you shouldn't see any rotation in the light. So once again, a chiral molecule would cause rotation in light. So for question 2, it says discuss your observations in the polarimeter part of the lab. So for my observations, this is what I have. More importantly, these are the rotation light that I was able to calculate. And from my observations, I'm kind of seeing that everything is optically active because it has a rotation in light. But I will get to alanine in a second, later for question 3. But the second part of question 2 says, how could you know the molecules are optically active just by looking at the structure? So if I looked at the structure of fructose and dextrose and alanine, I would be able to determine if they're optically active by seeing if their structures are chiral or if they are achiral. Because once again, from question 1, we now know that chiral structures cause rotation in light, and rotation in light means that they're optically active. So by looking at the structure of dextrose and fructose and seeing that there is an angle that I was able to measure from the rotation in light, that tells me that they are chiral and that they are optically active. Now I'm going to get to alanine for question 3 because that says, how does the concentration, impurity, and identity of the substance affect the results? And I think my alanine is a pretty example of how the concentration, impurity, and identity can affect its results, because I got a 33% error. But what I put down for this answer is that showing a different rotation of light or showing no rotation of light because its purity shows that one enantiomer is more concentrated than the racemic mixture, which a racemic mixture is composed of 2 enantiomers. So what I'm saying is that one of the enantiomers is more concentrated than the other enantiomer when they're put together in the racemic mixture, making it not as pure of a solution. So in this case, I saw that there was 1 degree of rotation, which really isn't that much, but that little difference did give me a huge percent error, so it does make a difference. And so from that, I was this is why I think it's a good example, because I'm seeing that probably one of the enantiomers in this racemic mixture might be a little bit more concentrated in this mixture, and so that may have caused the 1 degree light rotation that I saw. So if they were completely balanced and even, I shouldn't have had any, and I shouldn't have like any percent error on that one. But so in that case, since it is supposed to be a 0 degree angle, and that means that there's no light rotation, that means that alanine is supposed to be achiral, meaning that it's optically inactive. Another way that I could have checked myself was also checking the structure to see, once again, if the structure was chiral or achiral.